Hello gentlemen, welcome to our video on Chapter 14, Chemical Kinetics. Now when we think about the word kinetics, we oftentimes think about motion or movement or energy. That is involved in this process, but we're going to kind of approach kinetics in a slightly different way. So chemical kinetics is the study of the rate at which reactions occur. So these chemical reactions, the rate of a chemical reaction. It also tells us not only the rate of reactions, but in the science of kinetics, we look at the process of which those reactions occur. So exactly how the reactions occur, and we call that a reaction mechanism. It's basically a step-by-step breakdown of how the reaction occurs from reactants to products. Now, reaction rates can be determined by measuring the change in concentration of either reactants or products. Let's take this example here and talk about how we can manipulate this in terms of changing of concentration over time. So if we look at this chart, we have our reactant here, C4H9Cl, and it's some given concentration at time equals 0. So at the very beginning of this experiment, there were 0.1000 molar of that substance. After 50 seconds, I now have 0.0905 molar. So my concentration has decreased. And that makes sense because, in a chemical reaction, your reactant concentration is going to decrease. It makes perfect sense. Now, to figure out the rate of that reaction, we look at the average rate of reaction, and we calculate that by calculating or measuring, the change in concentration over the change in time. So in this case, my change in concentration would be, from 0.1 to 0.0905, and my change in time would be from 0 to 50 seconds. And we know that, we can represent that with this equation down here, something that's, all very familiar with us, delta. So the change in this concentration of my reactant over the change in time. Now, we do see this negative sign here. This negative sign represents the fact that this is a reactant, and it is disappearing over time, meaning my concentration is going to decrease over time. Now, let's look at the same reaction and analyze it, further in terms of reactants and products. So in this reaction, the ratio of C4H9Cl to C4H9OH is 1 to 1. So here is my reactant to my product. This is a balanced chemical equation. Both of my coefficients are 1 for these two substances, so the ratio is 1 to 1. What this means is that the rate of disappearance of my reactant is the same as the rate of appearance of my product. So just as fast as my reactant is being diminished, my product is being formed at that same rate because it's a 1 to 1 ratio. We can represent that in equation form with this. So the rate is equal to the average reaction rate of my reactant, which is equal to the average reactant or reaction rate, of my product. Those would be equal to one another, except I have a minus sign here or a negative sign there to represent that it's a disappearing reactant. Now, what if the ratio is not 1 to 1? Now here we have to kind of use a little stoichiometry and think about this substance in terms of the balanced chemical, or this reaction in terms of the balanced chemical equation. So let's take this example here. I have 2 moles of hydroiodic acid decomposing into 1 mole of hydrogen gas and 1 mole of iodine. In this case, the rate equals disappearance of half of my change in concentration of HI over delta T, which is equal to the appearance of the change in concentration of I over the change in time, t. I could also add on the delta H here, delta H2 over change in time. I didn't there, but I could because they're both 1 to 1. Now, in general, how did I figure out this negative 1/2 here? Let's talk about that. In general, for any reaction, let's think of A, lowercase a, being my coefficient, and uppercase A being my substance. In this case, HI. So in this case, it would be 2 for the lowercase a and HI for the uppercase A. And the same with B and B, C and C, D and D. We take our coefficient A and we flip it, make the reciprocal of A, and that is what leaves in front of our average rate equation there. So just like I had a 2 up here, my original equation for HI, if I take the reciprocal or inverse of that 2, it's going to be a half. And because it's disappearing as a reactant, it's going to get a negative sign in front of it. So I have negative 1 over 2 times the change in my concentration of what substance? Well, my reactant that I'm dealing with, over some change in time. So gentlemen, that is how you would represent an average rate equation from a balanced chemical equation. We can talk next time about how we can incorporate stoichiometry into this and how we can take this further into what we call a rate law. Gentlemen, take notes.